Imagine this. You're at a sporting event, ready to enjoy a nice hot coffee. You crack open a self-heating can and boom, hot coffee ready to drink, or maybe you've sprained your ankle. You reach for an ice pack, squeeze it, and it gets magically cold. How is this even possible? Welcome to the fascinating world of chemical reactions and energy changes. These everyday wonders and countless others happen because of chemical reactions. These reactions are happening all around us, all the time. They are the fundamental processes that drive everything from cooking food to powering our cars. In this essay, we will unlock the secrets of chemical reactions and energy changes, giving you the knowledge to understand the world around you on a much deeper level. We'll explore how energy plays a crucial role in these reactions, and we'll even conduct a hands-on experiment to see these changes in action. So, buckle up, and let's dive into the exciting world of GCSE chemistry. What exactly is a chemical reaction? Simply put, it's a process where substances change into new substances with different properties. Think about baking a cake. You start with eggs, flour, sugar, all individual ingredients with their unique characteristics. Mix them together and bake, and voila! You have a delicious cake, a completely new substance. Chemical reactions involve the breaking and forming of chemical bonds, the forces that hold atoms together in molecules. During these processes, energy is either released or absorbed. This energy change is what causes the coffee to heat up or the ice pack to become cold. But here's a fundamental law of chemistry. The total amount of mass always stays the same throughout a chemical reaction. This is known as the law of conservation of mass. Now let's talk about the heat. Chemical reactions can be classified as either exothermic or endothermic, depending on whether they release heat into the surroundings or absorb it. Exothermic reactions are like tiny explosions, releasing energy in the form of heat, light, or sound. Remember the self-heating can? That's an exothermic reaction at work. Endothermic reactions, on the other hand, are like ice packs, absorbing heat from their surroundings and making them feel cold. This absorption of heat is why the ice pack gets chilly when you squeeze it. Understanding the difference between exothermic and endothermic reactions is crucial to grasping the role of energy in chemical reactions. Time to put on our lab coats. Let's do a simple experiment to investigate temperature changes in reactions. We'll use hydrochloric acid, HCl, and sodium hydroxide, NaOH, two common chemicals. First, gather your materials: safety goggles, gloves, a beaker, a thermometer, hydrochloric acid, and sodium hydroxide. Now put on your safety goggles and gloves. Carefully pour a measured amount of HCl into the beaker. Use the thermometer to record the initial temperature of the HCl. Slowly add the same amount of NaOH to the beaker while stirring gently. Observe the temperature change as the reaction occurs. You'll notice the temperature rise as the reaction proceeds. This is because the reaction between HCl and NaOH is exothermic, releasing heat into the surroundings. Section 5. Charting the energy journey. Reaction profiles unveiled. Now, let's visualize how energy changes during a chemical reaction using reaction profiles. These diagrams are like roadmaps for chemical reactions, showing the energy levels of reactants and products. In an exothermic reaction profile, the reactants start at a higher energy level than the products. The difference in energy is released as heat, represented by the downward slope of the curve. The peak of the curve represents the activation energy, which we'll discuss in the next section. Endothermic reaction profiles, on the other hand, show the products at a higher energy level than the reactants. This means that energy is absorbed during the reaction, represented by the upward slope of the curve. Section 6. The energy hurdle. Understanding activation energy. Imagine trying to roll a boulder uphill. You need an initial push, a burst of energy, to get it moving. The same goes for chemical reactions. Even exothermic reactions, which release energy overall, require a certain amount of energy to get started. This initial energy push is called activation energy. Think about striking a match. The friction creates enough heat to overcome the activation energy needed for the match to ignite. Once ignited, the match continues to burn, releasing heat and light in a self-sustaining exothermic reaction. Activation energy acts like an energy barrier that reactants must overcome for a reaction to occur, regardless of whether the overall reaction is exothermic or endothermic. Section 7. Bond breaking and making, the energy cost of reactions. Remember those chemical bonds we talked about earlier? Breaking and forming these bonds is at the heart of energy changes in chemical reactions. Breaking bonds requires energy. Think of it like pulling apart two magnets stuck together. It takes effort. Forming bonds, on the other hand, releases energy, just like those magnets snapping back together. The amount of energy needed to break a specific type of bond is called bond energy. By knowing the bond energies of the bonds broken and formed in a reaction, we can calculate the overall energy change of the reaction. Section 8. Exam Success. Mastering chemical reactions and energy. Now let's put your knowledge to the test with a sample exam-style question. Explain why the reaction between sodium hydrogen carbonate and citric acid is endothermic. The reaction between sodium hydrogen carbonate and citric acid is endothermic because it absorbs heat from the surroundings. This means that the products of the reaction have more energy than the reactants, as shown by an upward slope in the reaction profile. The energy absorbed is used to break the bonds in the reactants, which requires more energy than is released when new bonds are formed in the products. Remember to clearly define key terms like endothermic and reaction profile in your answers. Use diagrams to illustrate your points and provide specific examples to support your explanations. Section 9. Chemistry in Action, Real-World Applications. Chemical reactions and energy changes are not just confined to textbooks and labs. They are happening all around us, all the time. Burning fuels. Combustion is an exothermic reaction that releases energy in the form of heat and light, powering our homes and vehicles. Cooking, baking a cake, frying an egg, even grilling a steak, all involve chemical reactions that transform raw ingredients into delicious meals. Batteries. Batteries store chemical energy and convert it into electrical energy through chemical reactions, powering our phones, laptops, and other devices. Photosynthesis. Plants use sunlight to convert carbon dioxide and water into glucose and oxygen, an endothermic reaction that forms the basis of the food chain. Understanding the principles of chemical reactions and energy changes allows us to appreciate the chemistry happening all around us and to develop new technologies for a sustainable future. Section 10. Key takeaways, your chemical reactions cheat sheet. Let's recap the key points we've covered in this whirlwind tour of chemical reactions and energy changes. Chemical reactions involve the transformation of substances into new substances with different properties. Exothermic reactions release heat into the surroundings, while endothermic reactions absorb heat. Reaction profiles visualize the energy changes during a reaction. Activation energy is the minimum energy required for a reaction to start. Bond breaking requires energy, while bond forming releases energy. Chemical reactions and energy changes are everywhere, from everyday life to cutting-edge technologies. Armed with this knowledge, you're well on your way to acing your GCSE chemistry exams and unlocking a deeper understanding of the world around you. Keep exploring, keep questioning, and keep the joy of chemistry alive.